Hey everybody, my name is John Grimsmo and I have a problem. I love lathes. I love lathes so much. I bought that lathe, and then I bought this lathe, and then we just bought the Wilhelmin, which is sort of a lathe and sort of a mill. Mostly a lathe, but also a mill. But today we're going to focus on the Torno Swiss lathe. I want to give you guys a quick overview of how it works, why it works, what we use it for, and why we love it so much, and why I want a second one, but we're running out of room. So let's dig into it. These three components right now are the only things that are being made on the Nakamura lathe right now. Pen parts, the Saga clip, the slider, and the tube. The clip is a perfect Nakamura part, but it's actually a really perfect Wilhelmin part. So this is the reason I got the Wilhelmin. Very excited to transfer the clip onto there. The tube could be a very good Swiss part, but the Nakamura is doing a great job. We've got a long drill that goes all the way through. So Nakamura makes that part good. This also could be an excellent Swiss part, but it's kind of a big diameter. It's the upper range of what the Swiss can handle. And the Nakamura, it works. It works fine. So we just keep making that. Otherwise, we have probably 20 parts that are being made on the Swiss, different setups every week or so. All right, so these are the two main products we make, plus the Norseman knife, but it's the same hardware. So that's a lathe part, that's a lathe part, that's a lathe part, that's a lathe part. There's two stop pins in there, lathe parts. There's lock bar insert screws, lathe part, 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 lathe part. Like, we make a lot of lathe parts. Do you think like a lot of people are surprised when they're like, you make knives, why do you need lathe parts? Well, because we actually make every single component in every product that we make. And there's a lot of round stuff. Basically everything round goes into one of those now 3 machines. And there's a lot of parts. Let me show you how many parts there are. 2 spacers for every knife, 5 screws for the Rask, 7 screws for the Norseman, lock insert screws, 2 per knife, 1 pivot screw, 2 bearing cages, 2 stop pins, 1 thumb stud for the Norseman knife or a dual thumb stud, Saga pen tip, Saga pen button, Saga pen threaded sleeve, and also the tube, clip, and slider. So 2016, when we wanted to buy our first big boy lathe, I was extremely torn between buying a Swiss lathe or buying a Nakamura like this one. We ended up choosing the Nakamura. I'm still not positive if that was the right decision for the time, because our parts are this big and very detailed and very intricate, and this is a big, powerful, lathe. The Swiss is perfect for making those tiny details. This is better for making bigger parts, which I thought we would get into with flashlights and things like that. We just haven't yet. So it's not perfectly suited for everything that we do, whereas the Swiss is better. But now we're doing a lot of the pen parts on here, which it is perfectly suited for, and most of the knife parts and a lot of the pen parts on the Swiss. So we have a really good balance between the 2 machines. So I don't regret buying this one first, but I think we might be further ahead for our products if we had the Swiss first. And we might not have ever gotten that if it worked out like that. But no regrets, right? The Swiss, however, I mean, right now it's machining these Delrin plastic bearing cages. These go in our knife, 2 per knife. So it's nice for today because it's a dry process. We can actually film inside, we can see everything. Almost a year ago, we hired Pierre, who you'll see later in the video. He now runs our lathe department almost entirely by himself. I don't touch this stuff anymore, so I'm trying to remember how it all works. But let's pretend that we're a part. I want to show you the entire process from the bar to the finished product and how it flows through the machine and why this machine is so amazing for that kind of stuff. This is Pierre, and he's going to help walk us through the flow process of this part.
Almost everything starts here, the material rack. Okay. So those are all the bars that are going to feed either the Nakamura lathe or the Tornos. So today I'm making bearings on the Tornos lathe. So it starts with Delrin bars that come out of here. This bar is going to need to be prepared inside the lathe. So first thing, I'm going to load it inside the bar loader so it could go through the chucks and be machined in the working area.
And one of the things with the Swiss lathe is you have to prep every bar. Like, yes. See how this has a big fat chamfer on the end? Yeah. Even the plastic will need that too, right? Every bar has to be.
Basically, everything that's over 3/8 of an inch is going to need a prep because because of the gripper. Yeah, anything else, anything smaller is good to go. You have a specific gripper for each size, but yeah, only the big ones need the specific.
Yeah, that's right. So everything over 3/8, you have to actually turn a smaller diameter down to 3/8
I have an example here.
to be able to do that. Because this lathe is a 13 millimeter lathe, so it can run 13 millimeter bars, but you gotta do this to it.
Yeah, basically, this diameter needs to be small enough that it would fit the gripper. This one is a smaller one, but you get the idea. This needs to fit. So we turn it to a specific diameter that fits the gripper that's inside right now. And then, yeah, the loader takes care of it.
And every bar needs that big fat chamfer in the end because the guide bushing is a fixed diameter that doesn't expand and clamp, it just stays. So the bar has to, if there's not a big enough chamfer, the bar will like get stuck every time.
And the loader is pretty sensitive. Any force that is a bit over what it should give is going to trigger it and stop it. So even if you have a bar that is not really straight and has a diameter change on the length, it's going to, you know, jam into the guide bushing, and this guy is going to stop everything.
So for that reason, we run almost all the material is centerless ground, which means another company, you know, preps all the material, grinds it all to a perfect diameter within a few tenths usually across the whole thing. And ideally, each bar of a 10 bar run or whatever is the same diameter.
Yeah, it's not always the case.
Right.
I have to be careful when I load it with 4 or 5 bars that I don't give too big of a range, because it's gonna jam. And if it's too small, it's gonna wiggle and wobble and make oval parts and bad parts, basically.
Well, the whole purpose of this lathe is to make critical tolerance parts. So you look at the whole system, including the bar diameter, as a factor, right?
Yeah, every little factor is gonna, affect first the surface finish. That's the most obvious because you can see it, but also dimension. The fact that the parts are round is really critical for what we do, and this involves a lot of precise setup, like the guide bushing. Even the tools themselves need to be prepped correctly. To load a bar, you have here some endless screws, Archimedes screws. So those are going to be able to move to load or unload a bar. So basically, if I do that, imagine this one is going to be loaded. It's going to move it forward until it falls into the channel here. So the machine is running now, so it's not going to be able to do that. But this channel here is where the bar will sit. And then there's a gripper, just like this one. It's going to grab the end of the bar in there,
it's on there.
Jam itself, and then push the bar until it is into the collet and inside the guide bushings, basically until it's on the other side. When it does that, the machine asks to close the collet. So we're going to have a grab on the bar that we're going to feed into the machining area. Once we're there, we need to check that the guide bushing is actually tied on it. So there's a whole procedure for that. This is one of the most critical things on the machine. So it needs to be right. And then we're going to see it come over to the machining side, and we can start.
And then it starts machining.
Yeah, removing material.
And then the bar loader will constantly follow the main spindle, the main chuck, as it pushes the part through.
By the way, you have to give it the length of the part that you produce and the diameter so it can synchronize itself with the spindle. I've had cases where too big of a discrepancy and it doesn't know where it is and just asks what to do, because the spindle itself has enough power to move it wherever. If it pushed the bar back, the bar loader is not gonna, you know, yeah, it's gonna be moved by it.
Okay.
So the sensors get kind of lost if you know, if you don't tell it beforehand, basically.
So when we're making these thin little bearings, how many parts can you get out of a 6 foot bar?
Oh, out of 6 foot bar, I can have a calculation for you, but it's gonna be around 300, 350 parts.
That's awesome.
The thing is, the bearings, you can see they're super thin. They are in fact thinner than the parting blade that we use to cut them off.
So we're wasting more material.
Yeah, so we have more chip than actual parts, but that, you know, the part itself dictates that. So that's the spindle. I'm gonna move it back. Okay, so following the bar loader, the bar comes through this tube here. Inside this tube is gonna be the material, comes all the way through that, and it's gonna be grabbed by that. That is the collet. We call it the main collet. This is just so the bar is grabbed and moved back and forth and also rotated, okay? This technically doesn't need to be super concentric because this is the guide bushing that's gonna do that. It's hidden inside there. But yeah, it's less critical of it being centered than on a standard lathe, because on a standard lathe, this is what's gonna make sure that the part is centered on your, that you work on the center of your part. Yeah, so that's the guide bushing. This is the part that will make sure that everything is centered. It's not gripping, it's not moving, it's just keeping the bar center and make it slide in and out. I'm gonna feed the bar through so we can start a new machining cycle. All right, that's the starting point. A Swiss lathe is always gonna start with parting off, even if you have nothing in front of it, just because it's made to make parts one after the other, like all day long, all night long. So it started with parting off, making sure it's not gonna jam a tool into something where it shouldn't be anything.
So Swiss lathe is different than a traditional lathe. It's like backwards, where the part is actually moving forward into the cutting tools, and all of your turning tools, I like to think of my little fingers on the side here, like turning tool, threading tool, part off, whatever. All they do is they move side to side and up and down, whereas on that lathe they move in all 3 directions. So the bar goes through the, you know, the guide bushing and against the tools, and the tools don't move very much.
Yeah, so we can see, I'm gonna move the XY, so that's X. That's pretty similar with any other lathe.
In this position you have the part off on the back and you have the main turning tool on the front side.
Yeah, exactly. So we have, this is a first side and the second side. So that's X. We can also move in Y to expose different tools. Okay, if I want to go with the burnisher here. Yeah. And then Z, instead of coming in and out like that, we're gonna have the bar itself, the material coming in and out of the guide bushing. That's the Z axis. And that's the biggest difference between the Swiss and any other lathe.
And typically with the Swiss, like with other lathes, you want to do roughing passes, like zip, 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 when you're making the diameter smaller. With a Swiss, it's like one and done. It's like you turn the entire profile in one shot.
The thing is, having the guide bushing that makes sure that the part is stable and centered makes the cutting action.
Your guide bushing right here and your cutting tool right here.
Yeah, and the distance is always the same.
Right.
It's not like you're gonna have a longer stick out if you make a longer part. What means is you can hog a lot of material. It's a very rigid setup, and you eliminate the whole bar flex that if you machine a very long part, you're gonna have on it.
Yeah, like this exactly. If you were gonna turn this diameter, it's gonna wanna wiggle. It's gonna wanna chatter and vibrate and stuff, but a Swiss basically lets you machine it like this and stick it out as you're machining it. And it's really rigid and really, really precise.
Yeah, and it's a very stable machine. It's made to be thermally stable and dimensionally stable.
it does warm up.
Oh yeah.
You notice, like,
Yes.
first part of the day on a cold day versus last part when you go home, it's what, a thou or something, but
It depends on what part, but usually, you know, the first 2 or 3 parts are automatic failure because the machine is still warming up, and if you want to try and touch the offsets, you're gonna mess things around. So it has to be warmed up, usually in 10-15 minutes. It's at a working temperature.
But you don't do a spindle warm up, you just make parts.
Not really, yeah, I make parts. Then if you use a very expensive material, that's probably a good idea, but then, you know, time versus cost, I guess. We're now looking at the sub tools, the sub side, we call it. It's the second side that is machined. After the part has been machined on the first side, this is the sub spindle, and it's gonna come close to the first one and grab the end, well, the part that has just been made, and it's gonna be parted off with this blade. Once that, we were in the second half of the machining of the part. It's gonna be held in there and going into the sub tools. So we start here. That is a facing tool. It's gonna make a nice clean face on the second side. Then we go to this, which is a chamfer tool. It's gonna chamfer the hole because the parting off leaves a jagged and usually not really aesthetic edge. And lastly, we have this tiny little tool. So that's a 1 millimeter undercutting ball. We call it a lollipop because it just looks like a lollipop. So this is gonna make the hole and cavity for the ball bearings to sit in. It has a very dancing around kind of tool path, but in the end creates a cavity in the plastic so the ball could fit. You can see them. You can see those holes. And those are not just straight holes. How to say that? They are made so a ball could pop inside. So I'm gonna take a ball. Basically, I want the ball to be held captive inside of the bearing. So I press it in, and once it's inside, it stays. So that's what this tool is made for, and it's made specifically for that, and it only does that. Once I go to another part, I just take it out and it'll wait for the next batch.
So while Pierre's doing this, I can tell he's got his mental checklist of, you know, make sure the bar's out, make sure everything's safe, make sure the door's closed, make sure everything's in the right mode, make sure we didn't open the collet when we shouldn't have, or
make sure there's no coolant because the plastic particles are a nightmare into oil.
Right.
All right, so we have the both sides working at the same time, the chamfer on the sub, and now it's gonna do those ball cavities. While on this main side, it has been drilled, the outside diameter has been turned with the chamfers, and now there's a boring bar bringing the inside hole at a very precise diameter that will fit on over our pivots.
So now the main side is done.
Yeah.
That was like 12 seconds.
Main side is waiting for the sub to finish the cavities, and you're gonna see the transfer. So once it's done, the sub is gonna come to this chute here, eject the part that is just finished. It's gonna come through all the way this conveyor belt and into our carousel. Once it's done that, it's gonna go to approach the main side, part it off to grab the next part.
So we were just talking that we don't actually sell a part that comes out of the lathe. It goes into an assembly, into the knife, the pen, whatever. So it's hard to justify like what each part's worth, you know?
Yeah, and like a day of the machine could be very different materials. I could have a full day of making copper tubes on the neck, and you know, it's way more expensive than machining anything else basically. So since we don't have a single part product, it involves a lot of calculation, I guess, and you know, man hour and
make good parts.
Yeah, as much as possible.
Lots of them. All right, so now that we've seen, you know, the process of how a part is made, how about you tell us what it's like to clean this machine, maintain it, chip management, especially once the oil is running. What's it like?
So there's two different processes, I would say. Right now we're running it dry, so that's mostly cleaning dust off. And the particularity of this plastic is it makes very tiny particulates, and they go into the coolant and then clog the filters and damage the pumps, etc. So what we're using now to avoid plastic going in the bottom is that we have a filter material in the bottom of the pan that will allow every tiny particle to be captured, and we just pull the whole mat and pull all the material with it. So that's a lot easier than what we used to do is every time have to vacuum every little hole in the pan because it gets clogged pretty easily. Otherwise, I would say 80% of the time we run it with oil. So that involves every surface becomes oily. Even the handles, the belt is gushing oil. So that's
because the oil never evaporates, whereas coolant will evaporate and leave like a little bit of a film, but oil is just like cooking oil everywhere.
Stays. Yeah, it just stays. Feels a bit dry to the touch, but it's always staying.
So what's it like keeping it maintained so that all the handles, the floor, everything just doesn't get...
Okay, so a lot of cleaning, just basically everything that's outside the machine can be just wiped. Sometimes a little bit of, on the handles I can use some Windex, for example.
Yeah, Windex works great.
Yeah, I don't want to have it inside the machine because it could react with the oil, and a lot of bad stuff could happen like that. Otherwise, the machine itself needs to be, I need to go into it to clean it. So for example, I have this door here that about once every 2 weeks I take off and just pull handfuls of chips that I have to clean. And what happens if I don't do that is the ball of chip is gonna get bigger and bigger, and the axis is gonna bump into it and get stopped and jammed. So it could potentially be bad for the machine, though it has a good sensitivity and stops itself usually. Yeah, that's a lot of hands-on, pair of gloves, and usually I have oil up to the elbows when I'm done.
Yeah, there's no way to avoid the oil. Even the parts coming out, you check a part, you're oily. You really got to notice how he's got not only paper towels but also like dedicated taped to the table, which he replaces every now and then.
And you can see this one. Although there's something on top of it, it's oily.
Yeah, I can tell by looking at it.
Yeah,
this is oily.
This has another life, and then next week I'm gonna probably swap it out.
And trying to make sure that oil doesn't transfer to the bathroom door handle, and you've got your own sink over there.
Oh yeah. That's also when I want to measure a part. So I usually grab it from here, and before I can measure it, you can see on the top there's a lot of dust and oil and grime. So this will go into a alcohol bath.
Look at that.
And then I dry it. Now I can measure.
Look at that. See, this is a process Pierre came up with, and he just showed me this morning. I'm like, that's brilliant.
So now I can measure it more accurately.
Right.
For width. I'm a bit under. I'll tweak it. All right. Okay. That's good for me.
Yeah, so you got your measuring tools, the various gauge pins, your caliper, your digital micrometer on the stand. Yep. This really helps because you can hold your part and then measure like that. And we got more measuring tools in the toolbox there. Yeah. Real quick, I don't think I've really shown the computer system we put here, but we have a mini PC here. We started with a Raspberry Pi, but this is just more powerful. And then the PVC tube with these 3D printed brackets shows the screen, and they go up and over, just so that there's nothing on the ground. No cords, no cables, no power, whatever, and it works. It's so weird. I haven't touched this lathe in many, many, many months. I'm like, how do you open it again? Okay. So right now we're making the Saga pen tube on this machine right now. Like these guys right here. One difference between a turret lathe like this and the Swiss that I want to talk about is that this machine is a dual spindle lathe, and I'll probably never buy a CNC lathe that does not have dual spindles, because your part comes out done. You don't have to flip it over and put it back in. But this machine, all the tools are here, so it machining this part while that part's chilling out, and then when this side's done, then it'll machine that side. So you're only allowed to machine one side at the same time, whereas the Swiss is nuts because everything's happening at once. The part on the main side is machining it at one, in the cycle, and also the sub spindle with the weight codes and everything is also machining. So it's like having two machines in once, whereas this is like 1, 2, A, B, and then part, eject, and then A, and then B. So when we took the same part from this machine and put it on that machine, it can be twice as fast, depending on everything. So that machine can be a lot faster. And sometimes there's less roughing because you just plow it in one pass. And it's typically tighter tolerance, easier to hit, nuts on there. Much more stable, yeah. Everything's tighter. You got the guide bushing with the tool like right there. There are a lot of benefits to it, which is why this machine is better for bigger parts. When we're making our little 440 screws, the knife screws on here, it did it. We've made every single product we sell on this machine until we got the Swiss. It's just better on the Swiss. All right, let's talk about money. So the Nakamura lathe we bought in 2016, and as is with the chip conveyor and with all the options we got, I think it was about $303,000 Canadian. And then 2016, we got this in 2019, 3 years later. This was about 330,000 Canadian dollars. But then that's not always the end of the story, because sometimes the rigging costs are on top of that, so an extra like $5,000 to get it here on your floor. We had this drip tray custom made for a friend of ours, or by a friend of ours. We didn't have that tray in the old shop when we had this, so we'd constantly like clean up underneath. We had it made here. That cost us 2 Saga pens from our buddy, so that worked out great. But things like the mist collector that sucks the atomized oil out of the air, because you don't want to breathe that stuff. So we did all the plumbing ourselves. It goes to a beautiful AeroX ARO 300. That's like $5,000 or something for that. Versus on this machine, we have the mist fit. We tried using the mist fit on the Swisses. We didn't find it was powerful enough, so we went with the big boy. But sometimes things like that, like there will be extra $5,000 costs, tooling, chip conveyor, oil. A drum of oil is $2,000. Like things add up, so you got to be prepared for that. It's nice when you can roll things into the financing, because then you don't have to come up with the $5,000. You get to like pay it off over 5 years. But just keep those things in mind. There's a lot to it. This machine will be paid off within a few months. I think like 4 months away. This will be completely paid off and completely ours, so that's cool. I still have a few more years of payments on the Tornos. But yeah, we got a lot of monthly payments. But it's good, we're making parts every single day. This thing runs, both of these machines, now that we have Pierre here dedicated to lathe work, both of these machines run every day, and the Swiss runs almost every night, as deep as he can until there's a problem or he runs out of bar or something. There's always little things that happen, but this machine is so much more productive than the Nakamura. It just is. Like we have the bar feeder on the back, which is an extra $15,000, $20,000, literally required for a Swiss. You can't run it without one, but that's kind of part of the whole package. So it depends on the kind of parts you're making. The Nakamura is probably more flexible. The Swiss is more dedicated. It's harder to program. It's more intricate setup. Setups can take hours. But once it's running, then it just runs and runs and runs and runs and runs. And you're making parts every few minutes. And you literally walk away, have lunch, come back, run it deep into the night. It might still be running still in the morning. I think our record cycle time on this lathe is 48 hours continuously without an interruption at all. And that's fantastic. So yeah, you need tight, intricate parts. Swiss, definitely look closely at that. I'm really glad that we have it. The other add-on we got for this machine, it comes with a very low pressure coolant that comes out all these nozzles, like 50 PSI. And it also comes with built-in 300 PSI, which can go through the spindle, the sub-spindle, the collet, but also through any lines. 300 is pretty good, but as you follow these hoses on the ground, this is our Chip Blaster 2000 PSI high pressure coolant that will spray the oil like a pressure washer kind of. 2000 PSI is a lot. So that comes through these hoses right here. This unit can have up to 8 different channels. We're only using 4 of them right now, so we obviously over-purchased because 8 is a lot. But this is about $10,000 or $15,000 and required for making the stainless, the titanium, the deep drilling that we do, things like that. So, you know, the base machine is going to be like $170,000, but you got to add the bar loader, you got to add the high pressure coolant, you got to add sometimes chip conveyor, mist collector. It's going to be $300, $350 before you know it. Also, I almost forgot. Since we're running oil, not coolant, white coolant in the other machines, oil is a flammable thing. So we are basically required, from a safety perspective, to install this fire trace system. And this could be $5,000 to $10,000. It's a fire extinguisher, literally. This little red hose actually goes through in the machining area and has a loop around, and it will melt at a certain temperature. So if there's a fire, if there's flame in there, it will melt. It's pressurized right now, so the sensor in the top knows that it lost pressure, and then it will spray the fire extinguisher in there and extinguish any flames, because it's literally dangerous, like terrifying. I've seen videos of Swiss lathes like poof, exploding on the inside, catches fire, burns to the ground. Not a good day. So this is, a lot of people who run aluminum or brass or whatever, they don't install it, that's fine. But stainless, titanium, those harder metals, they are more likely to ignite, to throw a spark. It's terrifying. So we got that, no questions asked. We also got it installed just the other week on the Williman right there, you can see. The guy came in, installed it, that was $8,000. I was on the fence because I didn't want to, but I'm like, we're gonna run oil, we're doing titanium, of course, like, we have to. So I'm happy now that I've done it, now that I've already paid it, and stopped thinking about it. So as you can see, I absolutely love lathes. I mean, between the 3 of them, we probably have almost $750,000 in lathes. They mean a lot to me, it's really cool. My first machine was a lathe, a CNC lathe, and I just adore turning. I want a t-shirt that says, I love lathes. Thank you everybody for watching. I enjoyed filming this video. Pierre had a great time too, and we will see you on the next one.